Hello and welcome back, everyone. Today we're going to talk about combinational and sequential circuits. Right off the bat, I'd like to mention that there are some prerequisites. You have to know about logic gates and the truth tables for the most common logic gates, specifically the AND, the NAND, and the XOR gate. Alright, so what is a circuit? A circuit is just composed of logic gates, and it's used for different purposes, mostly just to perform operations. So they are divided into different categories, as you have guessed, combinational and sequential. I'm going to talk about both of those. I'm going to mention half-adder and full-adders. I'm also going to go deeper into how they work. We're going to look at the truth tables, and we're going to try to do some practice problems. And also, we will talk about SR flip-flops, which is the cross-coupled NAND gate, which is an actual sequential circuit. All right, let's keep going. So, combinational circuits. So these circuits are basically used to perform basic operations like addition, subtraction, and multiplication based on the inputs that they received. The outputs are determined solely by the current inputs, so there's no memory of past inputs. Whatever you put in, you're going to get that same thing every time. You can think of it as a one-to-one function. If you remember from algebra, if you have let's have the y and x-axis. Let's say it's a x squared. It's that function. If you plug in a number, you're always going to get that one exact number. You're not going to get different numbers. If I have x is equal to 2, there's only one output for that. And that's always going to be the case. So that output will always be the same for a given input. All right, let's talk about the half-adder. They're used to perform addition of two 1-bit digits. They're usually composed of an AND gate and an XOR gate. We can see here, the bottom left, the circuit with logic gates. So we have our XOR gate and we have our AND gate. How does it work? So remember, this is going to do addition, right? So we have two inputs, 0, 1, and then we have two outputs, the sum and the carry. So let's say we had 1 and 0. What is that going to be? We're going to have 1 in the sum and 0 in the carry. This is logical, but we could also think about why that works. So the XOR gate, let's remember the truth table for the XOR gate. The XOR gate says, well, we only have 1 if one of those things, if the inputs are alternating, right? So if we have, if the inputs are alternating, right? So if we have 1 and 0, or we have 0 and 1, that is the only time we're going to have a 1 in the output. And the AND gate says that we can only have 1 in the output if we have both of these to be 1, right? So with that logic, we know that the only way that the carry out is going to be, this is the carry out, the only way that's going to be 1 if we provide 1 and 1 in the input. So if it's 1 and 1, it carries out. Now, why does that work? Let's try to actually add two numbers. Let's add 1 and 1. The result is the sum and the carry out, right? Now let's try to do that. 1 plus 1, well, in binary, when you do that, when you add them up, so let's say we're adding, let's say we have this binary bit. When you add 1 to that, it's going to turn into 1, 1, 0. Every time you have, let's say we have a bunch of 1s, when we add 1 to that, all of these 1s are going to turn into zeros, and the bit that is in front of them is going to turn into a 1. So if we did that calculation, we'd end up with 1 1 0 0 0 0. So with that logic, we can think about the calculation off to the left that we're doing right now. Let's think about that. When we do 1 plus 1, well, we're going to have 0 and 1, right? So that means that the sum is going to be 0 when we have 1 plus 1, and the carryout is going to be 1. Does that make sense? Every time we do because we're actually adding 2 bits, right? So when we do that, the sum is going to be 0 because, well, it carries over. The 1 carries over to the carryout bit. That is pretty much how it works. Alright, now let's go further down and explore. Well, actually, we could take a look at the truth table that I've written down over here. So what does the truth table show us? Well, it is pretty simple. It says the carryout is only set right here. The carryout is only set if both of the bits are 1. That means if we say 1 plus 1, then the carryout is 1. Because we can't store 1, 0 in a single bit, so we need a second bit to store that information, right? So that's pretty much it. Let's go to the next page and let's do an exercise. So let's say we have let's say 0 and 1. What that means is that we also have a 0 and 1 here, and we have a 0 and 1 here. It's always a good idea to write down these values to the point of the logic gate so that we can actually illustrate and visualize what's going on. So the XOR gate, we remember, the XOR gate is going to be, when is it going to be 1? It's going to be 1 if the values are alternating, right? So it's either 1, 0 or 0, 1. Now, that means this is going to be 1, correct? All right, so what's the AND gate truth table? We remember it's only 1 if both of them are 1. Well, we only have 1, and we have 1 and 0, so this is going to be 0. Nice. All right, let's keep going. I think it should be easy for you to fill out this truth table because it is just very straightforward. If we have 0, 0, the sum is 0, carry is 0, 0, 1. Well, sum is 1, carry is 0, 1, 0, it's 1 and 0, 1, 1. Sum is 0, carry is 1. All right, I think it makes a lot of sense. And always, when you look at these truth tables, you notice that there's this interesting thing that's going on. Every time it goes down, every time you go down the chart, you add 1 to the values. That is why it's sort of alternating between them. 0, 0 plus 1 is going to be 0, 1. And remember, previously I mentioned when you add 1, this 1 is going to become a 0, and in front of it, it's going to be a 1. And it makes sense. I'll show you why exactly it makes sense. This is just a nice idea that will always help you to fill out these truth tables. So, I wanted to show you why it makes sense. So if we remember from our binary powers, let's say 4, 2, 1, 8, 4, 2, 1. So if you, let's say, have the number 6, so that would be 0, 1, 1, 0, right? This is in a binary. If we have that number, when we add 1, well, we're just switching that bit, right? That bit is switched. However, if we had, let's say, the number 7, which is going to be 0, 1, 1, 1, well, that is that number over there. So if you had 7 and we wanted to add 1 to it, what would happen? Well, let's see. Add 1 to it. Well, the first guy is going to be 1 and the rest are going to turn into 0. So this idea is very nice, and it's always going to be helpful when creating these truth tables. Every time you see a bunch of 1s, when you add a 1, when you add a 1, the 0 in front of those 1s turns into a 1 and the rest are turning into zeros. And if there is a 1 in front of it, well, if it was just a bunch of 1s, of course, we just have an additional 1 over there, and these others would just turn into zeros. Easy. All right. That was just a tangent, but I think it might be useful when you try to work these truth tables. Every time these inputs go down, they are just added by 1, and the way we add 1, I already mentioned. And let's talk about the FullAdder. So the FullAdder is just 2 half-adders and 1 OR gate. So if you want, you can take a close look at how it works. You can trace You can trace the circuit and figure out why it works and how it works. But however, what this does is it's basically just taking an additional input, and that additional input is the carry in. So where do we get that carry in? Well, remember from the HalfAdder, we have a carry out, but we're not using it at the moment, right? When we have just a single HalfAdder, that carry out is just sticking out there, right? It's not used. However, if we use another HalfAdder, we can actually build a FullAdder that can take on that value. So if we look at the bottom left corner, we can see that we have a carry in. So that is going to take that carry in bit, the carry out bit from the HalfAdder and put it into the FullAdder. So now we will have 3 different inputs, A, B, and C. And now when the addition happens, it's going to take into account all of those different values. So let's go down. All right. Yeah, so it is always a good idea to think about the FullAdder as a black box, because you don't want to confuse yourself with all of these logic gates, although it is always a good idea to trace these. Try to have some, different inputs and try to think about how that would work out. However, you can always think of it as a black box and try to get the results that way. So let's say, I'm going to remove these values at the moment. Let's say we have, we're adding 1, 1, and the carry in is 0. So in this case, what will happen? Well, this is easy, right? We know that the sum is going to be 0. C out is going to be 1 because we're carrying out. Now, what would happen if we actually did have a carry in? So we're adding 3 different bits. Now, that is very interesting, right? Let's try to do that. Let's try to do that down here. 1 plus 1 plus 1. Now, so we know this is the sum and this is the carry out, right? So what would happen really? So when we add both of these guys, we have a 0 in the sum, right? However, we also have this guy over here. So sum is still going to be 1, because even though the 1 plus 1 resulted in 1, 0, and the sum would be 0, we still have 1 more to add. So that is going to be, that's going to easily become 1, 1. Now, why does that happen again? Because when we added these 2 guys, let me clean it up so I can explain it again. When we added these 2 guys, we had a carry out over there, right? So that carry out, and then this guy over here is standing alone, so it goes down to the sum. And then we know that the carry out, the carry guy is now going down to the carry out, right? This explanation is a little spotty, but I think you might be able to get the general idea of why that works. And so you could play around with different values here, and we know that if we have, in this case, we're adding 0 plus 1 plus 1. So what do we know about that? We know that the sum is going to be 0, and the carry out is going to be 1, because we're adding two numbers. Again, 1 plus 1 over for the sum, and the carry out, sum is going to be 0. This is 1, because these guys, when they're added, one of the guys carries out. All right, let's delete that real quick. And so I encourage you to pause the video and try to plug in some numbers in this circuit and try to see what the outputs are. Remember to have the truth tables for all of these gates. So there are approximately, I think, six gates that you need to really know, and the truth tables for them. Once you have the general idea of how they work, it's easy to come up with the truth table. And with the trick that I showed you of how to actually add binary numbers, it should be easy. Now, if you take a look at this row, this portion of the table, you see we have 0, 1, 1. And then the next one is, we add 1 to the previous one, so the next one is going to be 1, 0, 0. See, that's that idea that I talked about earlier. That is how this entire portion, the input portion of the table, is created. So that is super nice. All right, sequential circuits. This is fun. What are sequential circuits? Well, these are more advanced, and they can remember the past inputs. So this is because they have memory elements built into them, and the output depends not just on the current inputs, but also on the past history of inputs. So like when you give it an input, it doesn't just consider your input. It also considers the previous input that it had. So that is exactly how it works. Now we're going to go more in depth in how this works, because I believe this is a little harder to conceptualize, to visualize in your mind, because this has a little tricky parts. All right, let's go. Well, I want to talk about SR flip-flops. This is the cross-coupled NAND gate circuit that we're going to talk about. There are different implementations of it, of the SR flip-flop, but the idea is generally the same. Let's talk about the SR flip-flop. All right, so we know that the purpose of this circuit is to store a single bit of data. The components used to make it is usually NAND or NOR gates. So currently we have two NAND gates, because this is the cross-coupled NAND gate. That is just a type of SR flip-flop. S stands for set and R stands for reset. And those are the inputs, set and reset. The outputs consist of Q and Q bar, which is which is just a way to say that they are complements of each other. So if Q is 1, Q bar is going to be 0, and vice versa. Now, it is important to know how this works, and I'm going to explain it in detail because I believe this is a little confusing. All right, let's actually take a look at the truth table first. We see that when S and R are both 0, the output values are unused. We do not care about them. They are never used. We know that, we can also see that when S and R are both 1, that is the memory state. Those can, that when S and R are 1, both 1, there can be two different values for Q and Q bar. It can either be 1, 0 or 0, 1. Now we're going to actually take a look at how that works. Let's go down. For this to make sense, we need to look at the NAND truth table. I've already written it down over here. So how does it work? Well, it is only 0 if both bits are 1. So that's all we need to remember. If A and B, which are the inputs, if A and B are 1, both of them, then the output is 0. Otherwise, it's always going to be 1. Now, why is that idea helpful for us? Let's see why that is helpful. Let's think about some values. Let's say 0 over here. Now, what does that tell us? That tells us this guy has a 0 input. That's the NAND gate. And it doesn't matter what this other input is. It could be 1 or 0, whatever it is. We already know if there's at least one 0 in the input for the NAND gate, this guy is going to output 1. That's what matters. Now, what we know, let's say this other guy has the reset is set 1. What we know here is that this is 1. And we also know that the second NAND gate gets its value from the output of the first NAND gate, right? So let's trace it. It goes from there all the way over here. Now we know that since this is a 0, this output over here for the first NAND gate is always going to be 1. And when we trace it down, we can see that this guy is getting a 1. So this guy has two 1s. All right. And we remember from the NAND gate truth table that when we have 1 and 1, the output is always 0. So this is now 0. Now what does this tell us? This tells us that when we have 0 for the set and 1 for the OR, those are our inputs, we can see that our Q is 1 and Q bar is 0. Alright, let's think about the other way around. Let's say R is 1 and S is 1 and R is 0. So what do we know about let's remove these as well. What do we know about the 0? This 0 is very important, right? Because that tells us, well, this guy's getting 0. And it really doesn't matter what this other thing is, right? What this other input is. It doesn't matter. This is always going to output 1. Now that is useful, right? Because now when we trace this out, when we trace it all the way back to here, we know that this guy is getting 1 here. And we also know this is getting 1. So this is 0. The output of the first NAND gate, which is going to be Q, is now 0. Now there is something nice that we can notice about this, and that is the fact that if we look at the diagonal values of both of these guys, we can see that they match, right? So S matches with Q bar and R matches with Q, and that was the case when S was 0 and R was 1. All right, that is really useful. It keeps just the idea here is that this basically the NAND gate, the truth table of the NAND gate really tells us why this works the way it does. Now that was the easy part. Let's now conceptualize about what happens when we turn R to 1 as well, because remember, from the truth table of the SR flip-flop, these two, when they are different, right? When S and R are complementary, when they're different, so let's say it's 0, 1, and 1 and 0. In that case, we have the Q, when S is 0, R is 1, Q is 1, and Q bar is 0. When S is 1 and R is 0, Q is 0, and Q bar is 1. Now, what happens when we have 1 for both S and R? Let's actually think about what happens in that case. Let's try to understand. Because, well, let's actually at first, let's realize that our previous values, these were our previous values, and then suddenly we changed R from 0 to 1. What's going to happen? Let's think about it real quick. So this is 1, and this value is 1. What is this going to be here? What is this value going to be? Well, we know that it is traced from here, right? That's coming there from there. And that's 1. We can see it's 1, so this is 1. Remember, when we have 1 and 1, the NAND gate is always going to give us a 0. Alright, so we can trace this other guy as well. So this is a 0 over here. So let's trace him back. Trace him back over to the second NAND gate. Well, that is going to give us a 0 over here. So 0 and 1, what is that going to be? 0 and 1 is always going to give us 1, right? In the NAND output. So this is going to this is going to create a feedback loop, and this state is going to keep staying like that. This state is not going to change as long as S and R are both 1. This entire portion is going to just keep that feedback loop and keep these values as they are before we turn both of these into 1s. Now let's think about a difference in the other scenario. Let's remove these values. I'm just going to quickly remove them. Okay, so let's think about what would be. So previously we had 1, 1. What did we have for those? Okay, yeah, we had 0 and 1. Okay, cool. So let's think about what would it be to have S as 0 and R as 1. Now, in this case, we remember when the NAND gate gets a 0 over here, it doesn't matter what this is anymore. This is going to be 1. This guy over here has a 1, but the second value it is going to get fed from here. So that's going to be 1. And that means that this is a 0. Now, remember the diagonal idea that I mentioned. These values are the same. So now, if we change S immediately to 1, what's going to happen? If we do that, we changed S immediately to 1. What will happen is that, 1 now goes into this guy, right? This is now 1 over here. And what's the second input for the NAND gate right over here? Well, it is getting that fed from here, so that's 0. That's 0, which means this is always going to stay 1 over here. And the second NAND gate is getting 1 over here, right? And 1 for the other guy, so this is always going to stay 0. So this feedback loop keeps that state intact. So pretty much what we want to do is whenever we have a certain state that we want to keep, first we set that state by setting let's say we want to set Q as 1. So you would set S as 0 and R as 1, and then when you have the state over here, what you're going to do, you're going to immediately change S to 1, and now this state is going to stay like that forever because of that feedback loop that the NAND gate creates for us. All right. There's one more thing I want to mention, and that is the fact that a lot of books and a lot of places, people actually have a bar at the top of S and a bar at the top of R. Now, why is that? Because when you look at the truth table, if we just make it bigger and take a look at it, do you see when you have S0 and R1, we're setting Q to 1. That means it is not the intuitive way when you would think of set to be 1, and then that would set Q, but that's not how it works. In our case, set is 0, that's going to set our Q to 1. So it works the opposite way. And you can see that in the truth table as well. All right, so that would be a good idea to keep an eye on. And pretty much a lot of places will have the bar to indicate that it's the opposite result of what you would imagine there to be happening. Because in reality, what happens in most cases, Q is what's used for the storage of the data, for the actual data that we're going to look at in the future. However, it really depends on the application of the system that we're building. Sometimes both of these are used. For example, if you have a motor, two motors, if Q is 1, it'll turn on the first motor, and if Q is 0, it'll turn off the second motor, and vice versa. So it really depends on the application, but it's always it helps to think of Q as the actual result that we're trying to remember, that we're trying to use in the end. All right, that concludes the video. I hope that was helpful, and if there are anything that you'd like to get a clarification on, shoot me a message or comment below. That's it. Thanks for watching.